Let's now move on to clustering. So what is clustering? Clustering is a fundamental machine learning task aiming to find groupings of objects so that the objects in the same group will be similar or more related to each other. And those in different groups will be different or less related. For example, here are some well separated data points, right? So they naturally form good clusters. And we can see that the intra-cluster distances are minimized and the inter-cluster distance are maximized. So these are the ideal case where it works. Clustering task is very easy. So one of the fundamental clustering algorithm is the k-means algorithm. So it works through a very simple procedure. Suppose we have these data points in a 2D space. The first step is to pick some seeds. That's the initial. Suppose we are going to cluster them into two clusters, right? So two clusters. So we first do a random initialization. We call it seeds. Pick two seeds as the initial centroid for the two clusters. Then we reassign the cluster. That is, if a point is closer to the red, then we will assign them to be the red cluster. If one point is closer to the blue, then it will be blue. So after we reassign it, this is the next iteration of clusters. Then the next step is to recompute the centroid. Right? So here we recompute the centroid for the red points. It becomes here, the red cross over here. Then we recompute the centroid for the blue points. Then it becomes here. Then the next step is to reassign the clusters, and then recompute the centroids. This is the updated centroids over here. And then we reassign the cluster again, and we find none of the points are reassigned. That this means the clustering has converged. So this is a very simple algorithm, and it works very well when the data are well separated. So the objective of k-means clustering can be written as to minimize the within cluster scatter, written like this. So you may notice this is similar to the PCA, and it also measures the spread or the scatter of a set of points around their center of mass. That is a mean. But here, the mean is for each cluster J. Right? So that is the k-means objective. And we can also draw some nice analogy to our previous machine learning tasks. For example, it is analogous to classification. It can be considered as classification without labeled training data. So the cluster labels are analogous to the class labels. And we can also consider clustering as some extreme dimensionality reduction, that is to reduce the data to a single cluster label. So we will finish the introduction of k-means here. because it's very simple and we don't go into much details. And here are the key ingredients for k-means clustering. So it models a linear separation between clusters. There's only one hyperparameter, that is the number of clusters k. And the parameter we are learning are the k cluster centroids. That's what we are updating in each iteration. And basically what it is trying to minimize is the within cluster scatter. And the optimization of assign the cluster, then compute the centroid and repeat is kind of expectation maximization optimization method. And there is also kind of gradient descent. And we notice that k-means is basically centroid based, and it aims to optimize compactness through the scatter, minimize the within cluster scatter. But there's a problem if the data structure are not that linear. For example, here shows two circles, right, which naturally formed two clusters. But k-means cannot separate these two clusters. Instead, it will determine a more linear separation of the two clusters. And for this example, the result is very bad. But there is another clustering method called spectral clustering, which models the connectivity between data, and it can cluster these two circles perfectly. So next, we will look at spectral clustering. So spectral clustering models data using graphs. So basically, it models each data point as a node, and then or points, right? So you basically group those points or those nodes based on their connectivity, which are the links, right? So the links in a graph. So the links connect two points or two nodes together. So that is the data structure for spectral clustering. It basically have model data as a graph. And for example, we can view the image segmentation problem as a clustering problem, where image can be modeled as a graph by treating each pixel as a node or a point in a graph. And then the separation of the graph is basically a clustering that segment the image into different regions. So how to create this graph? So a very popular way is to use a Gaussian kernel to compute the similarity between objects. So there's a hyperparameter sigma defines the spread of the kernel. So with this kernel, we can construct either a fully connected graph, right? So this is analogous to the fully connected layers, where we compute the similarity between all the objects. But this can be very expensive for a large graph. So another choice is to create a k nearest neighbor graph, where each node is only connected to its k nearest neighbors, and we ignore the rest. So this is analogous to the convolutional layers which has local connectivity. And then in this formulation, our clustering becomes a graph cut or graph partition problem. That the clustering becomes how to cut the graph into two or more. And the objective is to minimize the cut, means how many links we have to cut in order to partition the graph. Since we want to minimize the cut, a simple solution maybe we just pick the cut that will destroy the least number of links. But this will give a trivial solution where the algorithm will just pick to separate a single point. Right? So that is not a good solution. And a good solution is to normalize the cut. This is called the normalized cut. And before presenting that solution, let us look at the graph clustering process. We start with data. This is given, and then we need to construct a similarity matrix by computing the similarities between these data points. And this, after computing this similarity matrix, we will naturally define a graph over here. The connections between the data points are weighted, and the weight is the similarity. And then the objective of graph clustering is trying to separate these nodes into different clusters. And after the separation, so basically the nodes can be sorted into different clusters. And then if we have the similarity matrix ordered by the clusters, they will form these nice squares, checkerboards. And in graph clustering, we have to define some key terminologies. The first one is the degree of nodes. The degree of the nodes is simply the summation of all the weights connected to that node. So in the similarity matrix, this is equivalent to sum up the whole row corresponding to that node. So this is the degree of a node. The second concept is called a volume of a set. So that is defined for a set of nodes. For example, set A over here. So that is defined by all summation of the degrees for all the nodes belonging to X. That is equivalent to a square in the similarity matrix, including all the nodes for that set. So it is the volume. And let's consider a partition of a graph into two parts, A and B. Then we can define a cut, A and B, which is the summation of the widths of the edges that connect the two groups. So that is cut A and B are the summation of those edges with one node in A and another in B. For example, here, what is the cut between A and B? So by this definition, the cut is simply 0.1 plus 0.2 and equals to 0.3. And the goal is to find the partition that minimizes the cut. So we have said if we just minimize the cut, it will give you a trivial solution. And the good way is to do normalized cuts. And in this approach, we consider the connectivity between groups relative to the volume of each group, right? So that's why the relative to the volume, it means to normalize the cut, the connectivity. Right? So here is the definition of the normalized cut. You can see the cut is divided by the volume of set A and set B. And you can, the cut AB are the same, so you can take it out and rearrange into this definition of normalized cut. And here is the illustration. So suppose this is a volume of A, this is a volume of B, and the cut should be the same for this for A and B, and then basically we divided the cut by the whole volume can give you a good measure of the cluster. And to solve this normalized cut problem, we need to compute the similarity matrix W, and then we compute the degree matrix, which is basically the degrees for each node, and as defined in the previous slide. And then this normalized cut problem will be relaxed to a generalized eigenvalue problem like this. And if you are interested, you can go through the paper or some other references to know how we formulate this generalized eigenvalue problem. And here, G minus W is called the Laplacian matrix. And we can see eigenvalue problem is again very important in clustering. And then with this, by solving this generalized eigenvalue problem, we can obtain the clustering solution. And we can do a bipartitioning of the data points into two clusters by using the eigenvector corresponding to the second smallest. Right here, we're looking at the smallest eigenvalue that will partition the graph into two parts. So the second smallest eigenvalue basically have 1 point because it is a dimension is equal to the number of data points. So each element in the eigenvalue represents 1 data point, and it is basically sorted. And we just need to determine the split point. And typically, we can do this by plotting the normalized cut as defined previously for each of the candidate cut on a graph and determine which cut can give us the minimum normalized cut. But this will only give us a bipartition, that is to separate one graph into two. If we want to have more than two partitions, a popular way is to do a k-means clustering of those multiple eigenvectors. And basically, we treat that multiple eigenvector as a representation or graph embedding of the input data points. So this is a kind of dimensionality reduction of the input data points into elements in the eigenvectors. So this may remind you of some of the very big ideas in the literature of machine learning, such as logistic regression also transforms a classification problem into a linear regression problem of the logos, and it models the probability of the predicted outcome instead of the output itself, which is a binary class label. And similarly, in spectral clustering, we can basically transform a nonlinear clustering problem. Reminder of the two-cycle problem is a nonlinear cluster problem because a line cannot separate the two clusters. So spectral clustering transforms nonlinear clustering into a linear k-means clustering of the generalized eigenvectors. And these eigenvectors are based on the similarity graph, which models the connectivity of data points rather than the data points themselves. So this finishes the introduction of spectral clustering. So spectral clustering ingredients include the standard data preprocessing, and its structure is modeling a spectral separation between clusters. So they are non-linear separations between clusters. And there's a hyperparameter as standard. We need to determine the number of clusters k, and another possible hyperparameter is number of eigenvectors we want to use, but this is typically set to the number k. And to construct the similarity graph, we also need to determine the kernel bandwidth sigma. And what we are learning, the parameter are the generalized eigenvectors. And here, what we are trying to optimize is trying to minimize the normalized rough cut. And the optimization is still closed form through generalized eigen decomposition. And also, we will use expectation maximization in k-means if we want to have a k-way partition into more than two clusters. So these are the introduction to two of the very fundamental clustering algorithms. In the last session, we take a look at a deep learning model for clustering called autoencoder.